Welcome back. We continue today with the description of fluid flow, and we'll cover in this the graphical description and the fluid flow analysis. Graphical description of flows is important because our understanding of the complex motion of fluid is best obtained through it. It demonstrates fluid behavior and it helps us understand the geometry of flow and its spatial and temporal variations. There are a number of concepts in graphical description. One of the easiest one is the path line. The path line of fluid element A is simply the path it takes through space as a function of time. Consider a fluid element starting at RO at time t is equal to 0. As time proceeds, this particle moves. At any time t, its location R is given by R is equal to R naught, the original position at time t is equal to 0, plus integral of V dt from 0 to t. We have a number of particles, so we have number of paths, one for each particle. In this picture, we are showing the waves in ocean. How are the particles moving? If we look at this, the particles are moving like this. On the top, you can see the wave motion. But we have marked a few particles with black dots, and we can see their motion is strange. Let's look at two particles and their path is along two circles. So the particles in this are moving purely in circular motion. So paths of the particle are circular even though the waves appear to be traveling to the right. This is a time exposure picture of the same motion. Here a number of particles illuminated by a white light are captured moving in circles. The particles near the top are moving through circles of larger radius, and particles near the bottom are moving through circles of smaller radius. This is of course the Lagrangian concept as discussed in the last chapter. Lagrangian is the material description where we follow the particles and move along with them. Let's do an example. Sketch the path lines for a flow with velocity field V is equal to yi plus 3/4 tj. The velocity dx by dt is equal to vxt, a vector equation. The two scalar components are dx by dt is equal to vx is equal to y, and dy by dt, which is vy, is 3/4 t, the j direction component of velocity. And the integration of this yields very easily y is equal to 3/8 t square plus a constant c1, and x is equal to 1/8 t cube plus a constant c3. We can plot this for given value of c1 and c2. We can plot these path lines for different values of c1 and c2. Here we are starting with 5 values of c2 from -3 to 1 and value of c1 as 0. The path of 5 particles are shown in this graph. Next we talk of a streak line. A streak line through a space point A is defined as the locus of all particles which have passed through the point A at any time between substatic time and the current time. Thus, The plume of smoke coming from a chimney is a streak line, because every one of the smoke particle was at the mouth of the chimney at some time t earlier than the time at which this picture is taken. The streak lines that we saw in the Reynolds experiment are streak lines because all the particles are emitting from the same orifice of the jet. These are the streak lines of flow past an aerofoil. This model of the aerofoil is subject to a flow from the left to the right. At number of points upstream, we inject smoke. And so each one of these lines on the left is a streak line. And we see the streak lines do tell us how the flow is behaving. We see that the flow behind the aerofoil is kind of braided up into two braids of streak line, one at the top end, one at the bottom end. These we will learn later on are called the trailing vortices and are principally responsible for creating induced drag on this aerofoil. Here again is a picture where a delta wing is in a wind tunnel. The smoke is injected from the bottom, and we can see how vortices are shed alternately from the two ends of the delta wing. You can see the power of visualizing the streak lines. They tell us the nature of the flow. Let's here do an example. Calculate the streak lines for the velocity field v is equal to sine t I plus j passing through the point 0, 0, starting at time t is equal to 0 and ending at time t is equal to 10 seconds. This is a little complicated problem. Every particle must pass through point 0, 0. So the streak line at time t is equal to 10 seconds consists of the location of all the particles that pass through point 0, 0 between time t is equal to 0 and t is equal to 10 seconds. The particle at time t is equal to 10 seconds is still at point 0, 0, and the particle that passed through point 0, 0 at time t is equal to 0 second is at the top end of this streak line. So the method of calculating the streak line is that we find the location of the particle at time t is equal to 0, which passed through the origin at a given time t prime between 0 and t. Then we find the current location of all these points. We first determine the equation for the path line using dx by dt is equal to vx, which was sine t, and dy by dt is equal to vy, which was 1. The particle that starts from x naught and y naught at time t is equal to 0, by direct integration, this gives x is equal to x naught minus cosine t plus 1 and y is equal to y naught plus t. The starting location at time t is equal to 0 of the particle which is at time t prime at x is equal to 0 and y is equal to 0 is given x naught is equal to cosine t prime minus 1 and y naught is equal to minus t prime, because it was the x and y are 0 at time t is equal to t prime. So we plug in the equations in line 1. And from this we obtain x naught is equal to cosine t prime and y naught is equal to minus t prime. These are the location at time t is equal to 0 for the particles which are at x is equal to 0 and y is equal to 0 at time t prime. The current location of these particles at time t are then found by these equations, where we put these values of x naught and y naught to obtain the current location as x is equal to cosine t prime and y is equal to minus t prime plus t. These give the current location of all the particles which are at x is equal to 0 and y is equal to 0 at time between 0 and t, which by definition is the streak line through 0, 0. So we can find out the equation of streak line by eliminating t prime from this. And if we do this, eliminating t prime from the 2, we get x is equal to x prime plus cosine y prime minus t plus t minus cosine t. And this streak line, the origin at time t is equal to 10 seconds, is obtained by plugging in the value of t as 10 to get this expression. This is plotted as this. So the streak line for the given problem at time t is equal to 10 seconds, which passes through point 0, 0, is this. The third important concept in graphical description of the flow is a streamline. Streamline is a trajectory of the velocity field, much like the trajectory of a magnetic field or an electrical field. The local velocity vectors are tangent to a streamline throughout the flow field. In two-dimensional flow then, dy by dx, the slope of the streamline at any given point would be Vy by Vx. Streamline is an Eulerian concept. It does not track particles. In a steady flow, path line, streak lines and streamlines are identical. But when the flow is unsteady, these could be very different. This picture shows the streamlines in a steady flow. In fact, these are streak lines. These are a streak of smoke emitting from a rake to the left of this figure and flowing past an aerofoil. The flow is very well behaved. The flow is laminar. But these streak lines are also streamlines because the flow is steady. But if the flow is unsteady, then streamlines could be very different. The same flow we made unsteady by keeping the camera fixed and moving the aerofoil. And if we see the velocities are tangent to these lines which is shown there. Let's do an example. Find the equation of the streamlines for the flow given by the velocity field V is equal to x into 3t plus 1 I plus 2y into j. As we know, the slope of a streamline in two-dimensional flow is dy by dx is equal to Vy by Vx, and Vy is 2y and Vx is x into 3t plus 1. And this differential equation is easily integrated to give y is equal to c, a constant of integration, into x raised to power 2 divided by 3t plus 1. I plotted the streamlines for two different times. You realize that this equation between y and x changes with time. The solid lines are streamlines at time t is equal to 3 seconds, while the dashed lines show the streamlines at time t is equal to 6 seconds. As the time increases, the x component of velocity increases, and so the streamlines are much flatter at a larger time than they are at a smaller time. Another associated concept is a steam tube. If we take a small circuit C within the flow field, then there is a streamline passing through every point of the circuit. And these streamlines would form a surface enclosing a small thin volume with a cross section equal to the circuit C at that location. This surface, which consists of streamlines, is called a stream surface, and the volume enclosed by this closed surface is called the steam tube. Clearly, since the velocity is tangent to streamlines at all points, the velocity is tangent to steam surface at all points. This concept of steam tube we'll use in a later chapter. As was said before, there is a steady flow. The streamlines, streak lines, and path lines are identical. This picture shows a slender body in which smoke is being emitted through various orifices arranged in a line, and we get a beautiful picture of vortex. The flow is steady, so these streak lines are also streamlines as well as path lines. Can two streamlines intersect? Suppose they intersect at a point P, then clearly the tangent to a streamline is in the direction of velocity. There are two directions of velocity at point P, one along one streamline and the other along the other streamline. Clearly, that's not possible. The velocity can have only one direction. This is possible only if the velocity at point P is 0. In that case, there is no direction to a velocity, and the two streamlines intersect. Such a point is a stagnation point, where the fluid is stagnant. You see, the streamline at the nose of this body is dividing into two portions, one going along the upper surface and the other along the lower surface. So this point is clearly the stagnation point. The velocity at the left tip, the upstream tip of the aerofoil, is clearly a stagnation point. Can path lines intersect? Can streak line intersect? Yes, they can. Because if the two path lines intersecting, that does not mean the two particles are at that point of intersection at the same time. They could be at different times. So path line and streak lines intersect when the flow is unsteady. They cannot do so in a steady flow, because in steady flow there would also be streamlines, and the streamlines cannot intersect. Let's explain these differences between streamlines, path lines, and streak lines once again. Let us consider a point P in a flow field where the flow is from left to right. So the streamline would look like these arrows, black arrows from left to right. A particle at P would travel along this line. A particle that follows will also travel along this line. So this red line here would both be a streak line as well as path lines, besides being streamlines as we started out with. Now at time t is equal to t0, the direction of the flow changes. And now the flow is inclined at 45 degrees in that direction. If everywhere the flow direction is same, then the current pattern of streamlines would be these dark black lines. But the particles which pass through the point P up till time t is equal to t naught are still occupying this line. But now they start moving down in that direction. And so what is the final position of the particles? Those particles which pass through point P up till time t is equal to t naught is this. And the particle which pass through point P after time t is equal to t naught are along that inclined green line. So the green line is the streak line at this point of time. The green line is the streak line at this point of time. And what is the path line of the particle that started out first from point P? The path line is this blue line. They start from P horizontally and then take this 45-degree inclined line. So the green line is an inclined L, and path lines are inclined L upside down. I hope this clarifies the differences between streamlines, path lines, and streak lines. I invite you to watch this famous video by Professor S. Klein of Stanford University. This was made in 1960 and demonstrates the various flow visualization elements very beautifully. This video is available on YouTube and is also available on a site of MIT. I've given here the link.